Hey guys, how's it going? Welcome to another episode of Ferris Makes Emulators. This is episode 22, where I hope to be extracting a particularly plaguing sample that we've dealt with a bit before. But I need to gather some more info to see if we can finally fix some of these bugs. Base Effect, Trilater, Creekpot, Soda Design, how's it going, guys? By the way, I just about died at this very, very funny picture that I saw on Twitter. And I don't know why I think this is so funny. I guess it's because my humor is just that childish. But I really think it's funny. I'm sorry. It was about the right time for me to start, though. Echo Nim, how's it going? I'm just going to share this because I think this is really funny. It's one of these things that the more you look at it, the funnier it gets. How's it going, Dana Collin? My personal favorites here are Screamful Terror and the Log Brothers. Sorry, I just found this super funny. All right. Time to be super serious. CP3 Best, how's it going? Still laughing at Screamful Terror. It's been one of those days. So this is what I've been thinking. This last week or so, it's been super busy for me, first of all, just like with work and just being exhausted generally. So I didn't have that much like headspace to really think about what I wanted to work on this week. But this last weekend, I was thinking about these stupid timer bugs again. And last time we left off, I basically decided that, or speculated, that the rest of the timer bugs probably couldn't be fixed unless we dug into the CPU cycle accuracy, because it seemed like when we were adjusting the timer interval based on how many CPU cycles it was pretty touchy. And for those of you that are unfamiliar with the bug that I'm referring to, I'll just show you. So in games like Virtual Pinball, let me enable my system audio here. Hope that's not too loud. Actually, I'll turn it down a little bit here. There's a sample that plays, and this also happens in Galactic Pinball. Or sorry, this is Galactic Pinball. Virtual Bowling. Where it plays these samples by basically on every timer tick, it updates the volume of one of the audio voices. Like this. But as you may have noticed, the sample plays a bit too slowly. Now, I did a lot of playing around with the timer implementation, about a month ago now. And basically couldn't get it to match up particularly well. I even took recordings of the original hardware and then compared that against wave outputs from the emulator. And I wasn't able to really adjust the timer implementation to something that I thought might be sensible and then still get it to work, or get it to be close enough. So I started adjusting the interval of the timer. And if we look at this this timer, there's basically two intervals at which it can basically count down a number at. And when that number gets to 0, then the timer will tick. And the large interval is 100 microseconds, and the small interval is 20 microseconds. Now, where does it say Ferris at the executive? That's totally the name of my computer. Oh yeah, it's in my terminal, isn't it? Yeah. Anyway, so I thought that in a lot of the documentation, they round up a lot of values. And in particular, I thought that might have been what they were doing with the small timer interval, because if I adjusted that interval to something smaller, we at least got really, really close to the hardware recordings with a little bit of phase shift that said it wasn't quite perfect. And that always kind of bugged me. But I thought, okay, well, since we're adjusting this timer interval based on like clock cycles, like right now it's at 400, and I think we got around 332, 333, and that gets pretty close. The problem is, after that, I went back and I tested Vertical Force, which is a completely different game, and noticed that the music in that game plays too slowly. Or was it too slow or too fast? Must have been too fast, like noticeably. So that clearly wasn't correct. So that basically proves that this timer interval is 20 microseconds, like the documentation says, because if we change this to anything else, then the music in some other games breaks, which is good because then we know that like that's correct. Unfortunately, the sample still didn't play at the correct rate. So I thought, Soding, thanks for the follow, man. Good to see you again, by the way. So I thought that then what else could affect this sample playback rate. So I was thinking about how a sample playback routine would work. Note that I hadn't actually disassembled any of this. But a sample playback routine would basically, like for every timer tick, it would like disable the timer so it wouldn't tick again. Then it would go and read a sample from memory, then set some register so that we would actually play that. And then Dana calling, if the game is virtual pinball, then adjust the rate. Yeah. I'll get to mid-naffing in a second. It's not that bad, but it's pretty bad. Anyway, so I thought that, so on every timer tick, it's going to go read a sample and then set a register value so that the audio output would change volume. Basically, that's it, right? And then that would just happen in a loop. So every time the timer would tick, we would get a new sample. Now, if that were to happen and the timer were disabled and then a new sample was read and the timer was enabled, then that extra bit of time that the timer was disabled could count towards like the time between samples, right? So then it would be sort of natural that the speed of the CPU would, like if the CPU were running a little faster, a little slower than the actual hardware, then that little gap of time would be faster or slower. And assuming, just because that's an unknown that we have because our CPU isn't cycle accurate, assuming that's relevant, then we should really have the CPU being cycle accurate before we tackle the timer again. However, I was thinking this weekend about it and thought, okay, even if we have that drift, maybe it's not actually significant. And so to test that, what I did is I made all of the instructions take 1 cycle. I made all the instructions take 2 cycles. I made all the instructions take 10 cycles. And I also tried 100, I think. And basically, if you make it too high, the sample will start playing slower, but it actually gets like choppy. Like it doesn't play like at something that feels like a slower rate. It just gets really choppy. But if you set it to like 1 or 2 or 10 cycles for all the instructions, the sample actually doesn't change its playback rate. Now that's pretty interesting. That means that this is basically probably not significant. At least like the CPU cycles being significant to the playback rate of this timer, or of this sample. Sorry. Gravewish, how's it going? By the way, speaking of Gravewish, I'm guessing this is the same Gravewish that commented on Rostendo and gave some awesome information about how the delay slot works that I still need to wrap my head around. But in the meantime, I'm focusing on understanding caches a bit as well. Anyway, shout outs to Gravewish because he recommended this wonderful book, which is Computer Architecture, Quantitative Approach. This is the 5th edition. This arrived in the mail the other day, and I've read a lot, especially the appendices focusing on the cache have been really, really useful. So thanks for recommending that. That's been a really fun read, and I hope to read a lot more of it because I've always been curious about how some of that stuff works. So I will also recommend that book just because it lays out the exact information that I was looking for, which is basically how do caches work, what do these terms like direct mapped, or n-way associative, what does all that stuff mean? It's really, really cool. Love Gravewish, the appendices are some of the best computer architecture references I know. So far, I agree. I mean, not that I know very many, but it's pretty cool. So thanks again for that. That was pretty cool. So also been thinking about caches. Jay Westfall, by the way, has been working on implementing rcache, and actually it's pretty good. Our implementation, actually, after having read this, I looked over and there's a couple details, but we've been talking about that on the Discord. But until we can test on hardware, there's some speculation that we just kind of have to make. And until we can test that, we're probably not going to make any more changes. Oh, CP3 Best missed the title. It's called Computer Architecture, A Quantitative Approach. I'll show it again. Bloop. I mean, it was a bit pricey because it's a big old heavy computer book, but definitely worth it. I actually used to carry around books like this when I was younger all the time. Like I was 12, 13 years old and just carrying these around in my backpack. And I kind of missed that too. So it's been good to buy one of these books again. So that's been really fun. So yeah, recommended read if you're curious about how computer architecture works, which is relevant to emulators for sure. Yeah, Dana Collin just posted a link as well, which is very helpful. And I don't know why I didn't do that, but thank you. So anyway, basically what the interesting thing is here is this stupid timer that I spent a ton of time like adjusting the interval and also trying to adjust the implementation is probably still the problem here, even though I thought that it was going to be the CPU cycles. The thing that bugs me the most about this, though, is that that was all speculation. And while I think that was pretty sensible, I think we actually just have to dig down and just really get at the details of how this sample playback works, what the sample actually looks like, because I think what we need to do is find out the exact sample rate of this sample. And then we need to find out the sample rate of the sample, and we need to find out the parameters of the timer while the sample is playing. If we can find, or the register values, if we can find out those things, we should be able to infer a little bit more about how the implementation should work so that we would actually have the timer ticks when we would expect. A little bit more information on that. I did also, once I realized that this was how it was working, I also looked into Mednafin's source code, and I noticed that their timer implementation was different in a couple ways. First of all, one of the things that they do is when you set a reload value, right now what we do is whenever the reload value is set, we just reset our counter to the reload value. One small difference that they were doing was that they would like load that reload value into an internal register, and then on the next down count tick, then it would actually load the value then. And I dug up some more documentation and checked, and that is actually how it's supposed to work. I have code that does that, but I also have some code on that branch that like breaks stuff. So I just stuffed that on a branch for now. We're not going to worry about that yet until we actually extract some of the data we need and see how significant that might be. But anyway, that part is correct, but there's some details about that I'm just not sure about. Excuse me. So that was one thing. The other thing that I noticed is that their implementation was, other than that, basically identical to ours. There was a lot of extra logic, but it basically did the same stuff. The only difference is that it would always down count the timer value, even if it was just reloaded. Now, what that means is that the timer reload then was actually interpreted as the timer reload -1. And the significant part here is that meant that there are actually less, like one less down count, I guess, one last countdown iteration in their timer than in ours. Now I made our implementation match and then match that just to see if that was significant. And what I found was that then the samples in this game and Virtual Bowling played too fast. Now the interesting thing about that is that then I looked at their timer rate, and instead of 400 clocks, they actually have 500, which puts their timer at 25 microseconds. Their timer interval at 25 microseconds, not 20. Now we know that that's wrong. And when I set but I wanted to see what happened if we basically set ours to that as well. And of course, what I found is that then the playback matches Mednafin's, which, as we've seen from that game and a couple other things, like if you look at the long plays on YouTube or whatever, you'll find that they play that too slowly. So in particular, the songs in this game sorry, I'm a little scatterbrained. The songs in this game and the songs in Vertical Force and Waterworld all play too slowly. So it's like they have their timer implementation wrong, so it actually down counts one less time than it should. And then they compensate by increasing this small timer interval, which is just wrong in a different way. Like it's not even with the compensation, it's still not correct for a lot of these games. Now, what's cool about that is like we've kind of rolled out that there's anything more insightful there. The bad part is that we didn't find the fix. But at least we know that we might be on the right track. So that's all the kind of context that's been leading me to think, okay, let's just spend the stream trying to get more information, in particular using the debugger, which I haven't really shown that much, I think. Yeah, so that's what I was thinking. So I'm thinking, again, we can use the debugger to actually extract that audio sample, and also reverse engineer enough of the sample playback routine so that we can figure out basically, like on a high level, how the sample playback works and what the register values of the timer are while the sample is playing. With those two pieces of information and then the sample rate of the sample, we should be able to figure out how long the timer actually takes between ticks, and then hopefully we'll be able to infer a little bit more about the implementation. Now, I expect this to take a little while today, so I don't know how much of that data, like how much inference we'll actually do today, but I do want to actually just get as much data as we can about what's going on here and just dig a little deeper. Lord Gravish, Hennessy, one of the authors, was actually one of the main founders of MIPS computer systems. Yeah, it's funny because the book mentions MIPS all the time, so you kind of guess, but I think it also says on the front cover. But that's really cool. I didn't realize it was he was that pervasive. He also says the -1 might not actually be wrong, since they might just assume the timer counts down immediately when it was set up instead of just following a cycle, and that is what they're assuming in MNF, and that's exactly how the logic works. Not familiar with the NEC V810, yeah. So this timer, just a tiny detail, is actually part of the custom hardware in the Virtual Boy. It's not necessarily part of the V810. It's part of the NVC, which is one chip that has a V810 core in it, and then a couple other things like the timer and some other things, which is pretty common around that time. But yeah, so that's basically what they're doing, is that they set the reset value and then count down, like yeah. But that may actually still be correct, but because everything else was so incorrect, I don't want to gamble on that, because that's not something that I've seen documented, at least. But it could be correct, so it may be something to keep in mind once we actually get a little bit more data here. Whew. Okay, so what I'm thinking I'm going to start with is actually like breaking on while the sample's playing in the debugger. Let me just run this and get to that point in before Daniel Collin mentioning save states. Okay. I'm gonna pause my system audio here. Or sorry, mute it. There. And I'm going to turn it down for myself as well. So the debugger doesn't actually pause the audio when it's paused, which is kind of silly, but yeah, it's fine for now. We just need to mute it. So now we're basically... So all I did was I hit F12, now we're in this debugger. Now remember, this debugger is pretty minimal because it's kind of hand-rolled for this, but it should help us get what we actually need. So I don't have the debugger commands documented anywhere, but I'm just going to poke around. I've done this, I think, a few times, or quite a few times when actually debugging things in the simulator, but it's kind of been funny that I haven't really done much of this on stream. So what I'm going to do is I'm going to set a breakpoint. So basically the hardware has a bunch of like hard-coded interrupt vectors. So when an interrupt triggers, code execution will be transferred to a specific address, and which kind of interrupt determines which address it's going to actually stop at. So what I'm going to do is I'm going to add a breakpoint, which is AB in this case, and then FFFE10, and that's the address of the timer interrupt. And then I'm going to continue, and then here we are. So now, if I disassemble some stuff here, I'm going to be jumping around a bit, so sorry if it gets a bit hard to see. But here, we are at this address, which means we actually got execution here. And then this is the actual code here. Also, you'll see after this, we see a bunch of this outward -1, R31, R31. That's, as you can see here, just a bunch of Fs, so there's likely nothing of value there, and that's followed by a ret I. So this is the actual interrupt handler here. However, this does typically what a lot of these interrupt handlers do. So each of these interrupt handlers is, I can't remember if it was 16 bytes apart or 32 bytes apart. I can't remember how far apart they are. But the idea here is that there's not much space between the actual handlers here. So typically what they'll do is they'll set up a different address and then basically just jump to it. In this case, it adds 28 to R3, which is going to reserve some stack space. And not really sure what this does. Oh yeah, it's pushing R1 onto the stack because it's going to clobber R1 here and then jump to it. And I guess this routine is expected to basically fix all that after this. But then we load R1 with an immediate value, which is FFF00026. The V810 doesn't have any way to actually load a 32-bit immediate. So it's always done in these two parts, move high and move A. This actually adds the values as well. And I believe this one gets sign extended, which is kind of annoying because that basically means that this one, if the highest bit ends in a 1, the highest bit is set in this number, then this actually has to be one more than it normally should be, so that when they're added together, that will actually work out to the right address. But in this case, since this one starts in with a 0 bit, then it's just going to be this address here. So basically what this is going to do if we step is it's going to, here, I'll just do step here. And then we're going to take the jump here. So this jumped exactly where we thought it would. And now we start digging. Danicala didn't say anything. Sure. So here what we're doing is it looks like it's basically just storing some registers, which is good. That's something we want to see. Storing some registers relative indexed in R3. R3 is usually the stack pointer in the V810, by the way. So that's where I'm getting that from. We also move some stuff into R8 or into R6 actually. Just seeing where stuff might be used, and it's going to read some values. Store some stuff here. Then store some more stuff. I'm just kind of talking out loud. I'm probably going to get a bit quieter when I start digging into this, unfortunately, but I'm just going to start reading this. It looks like it also reserves a bunch more registers. Call some subroutines. Yeah, restores the registers after saving those, and then we return here. So that's kind of the high level. I'm just going to copy a bunch of this so we have it down somewhere. And also one last thing at the end that I expect to see is here. We adjust R3 again at the end, which should line up with what we saw up here. This adds 28 to it. And I'm guessing if we followed that, everything that adjusts R3, that would work out. Don't have to do the math though, it just needs to basically look more or less correct. Debugger2, thanks for the whisper. I will check out that link later. Cool, so I'm just gonna paste this into here. I'm also gonna set my syntax to assembler because sometimes that actually works well. If I can remember where that is. I'll just make it kick assembler. Is that is not what I wanted. I'm still pretty clunky when it comes to Sublime, which is fine. Let's make it Rust. Why not? Yeah, sure, colors. That's good enough. So I usually typically start like just adding notes to this. And I'm also going to save this. I'm going to save this to my desktop. And now it just went back to assembler, but that's fine. We're fine. So I'm guessing it looks like it actually branches past this RATI a little bit. Just seeing this address here. So this is one of the really useful things. If you do a disassembler in your editor, make sure you resolve relative addresses and have them printed, by the way. Because like this branch offset, this is this plus FC. And it's like, okay, I could do that math in my head, but I could just do it in the assembler and actually print it here. So there's actually probably going to be a little bit more here that we want to copy as well. Just looking at some of this. And I don't know how relevant a lot of this is going to be. But we're just going to print out some more things here. I'm basically looking for an RETI, which I see here. Because that's probably where it's going to return from this handler otherwise. Yeah, this looks about right. Cool. Might add some new lines here just to kind of help see what's going on. Now, at this point, I'm probably just going to step through and see if there's anything that jumps out in terms of what's going on. I could also, another thing is I may want to set some watch points in some of the audio stuff. In fact, what I'll actually probably do is rebuild the emulator with logging, and I'll probably add some logs whenever the audio stuff is accessed so we can kind of get an idea of which registers it's actually modifying. That's just going to be a little quicker than adding watch points to all the audio registers. So I'll probably do that. I don't mind hacking the emulator when trying to just debug stuff like this because it's usually trivial stuff that you end up doing anyway. So we can just do that. So to do that, we need to build this with logging, first of all. I think that's how you do that. Oh yeah, the log stuff was split up recently. We can do log VSU. That's one we care about anyway. Whoop. That's not a U. It is a rounded vowel in many languages, though. Log VSU, is that not what I wrote? Oh yeah, Core has those features. CLI is here. Oh yeah, we add Core to this. Been a while since I did this. Arsenal, how's it going? Hey, thanks for the follow. Appreciate it. All right, actually, I don't think this will, yeah, so that runs. I'm using Rust. It's in my FAQ, by the way. Down below. So what I'm going to do is just go into the VSU now, and I'm basically going to log all the accesses to it, just as kind of a catch-all. And I believe that's going to be down here. By the way, disclaimer, I'm not at all claiming that this is like the best way to do this stuff, but this is at least something I'm pretty comfortable doing. So we're going to just do this. We could just do print line here just because this is temp anyway, but no worries. I usually prefix the stuff that I just hack in here with some stuff so I can see this a little bit easier. And we're going to do something like, yeah, VSU write byte. And we're going to do the adder here. We'll do this little cute notation. Oops. And that should do it. And now this, I expect this to be pretty busy. But I expect that when the sample's playing, we're going to get something that's pretty predictable. And sorry, I'm just going to leave my system audio muted so I don't have to mute and unmute. It's not going to really matter because we're just going to break into the debugger anyway. All right, so that was when the sample was playing. And you can see basically we're seeing a bunch of values that go into like 410, 450, and it looks like they're all the same. Now, my guess is that this is setting like the left and right volumes of one of the voices, because you can see that this data looks pretty like contiguous, like it's going to be a waveform. So I'm guessing that that's what we're seeing here. So that, if we look at our memory map, should tell us basically which voice is being used here. So 410 is voice envelope 1 data, and 450 is voice 2 envelope data. Now, it's actually a bit weird that it's using the two voices. I did not think that this was stereo. Could be wrong. Didn't seem like it. And I think it's a bit odd that it's actually using two voices. However, what this does mean is that these are the two values that it's actually changing every tick to play that sample, which is pretty much something that we expected to see. So that's good. Arsenal, are you working on this solo, Ferris? If this game gets big, will you work on it as a team or something? So I'm actually, this is a Virtual Boy emulator. It's called Virtual Boy. I'll post a link to the repo. I'm working on it mainly solo, but there are a bunch of guys that have been helping out, and I want to probably try and turn that into identifying us more as the Virtual Boy team, probably, instead of me and the other people, which is getting less and less accurate. But yeah, working on an emulator, not a game. Just making this game work in the emulator is what we're doing. So we're debugging the game. Sorry, Gravish. Links are disabled by default. I usually whitelist people that are regulars. So I can add you though, because I'm guessing you'll probably have some other insightful links as well. let me fix that really quick. Yeah, the Virtual Boy is stereo. I'm just surprised that the sample is stereo, and I don't think it is. So I think it's a bit odd that it's actually like using two voices to play the sample. I'm kind of wondering why that is. It's writing the same data to each voice, it looks like. So I'm guessing it's just playing the sample stereo, but it's still weird because you could have had one voice just in the middle. So I think that's a bit odd. Yeah, I'm pretty sure our audio emulation is pretty good by now. I'm just surprised to see it writing to both these registers. But really, if we add a watch point to one of these, we should actually be able to see a lot of stuff. So there I let it play a little bit longer. And the reason I did that was because I wanted to see if it only wrote those two registers this entire time, and it did. So that's interesting. Now, excuse me. The other thing what I think I'm going to do is I'm going to, like, before we got the certain what was I going to say? Before I got certain audio emulation features in here, we saw that when the sample was supposed to play, it was just like showing a DC offset. And so what I think is happening here is that it sets these two voices output to be basically like the waveforms are set up so it's basically playing DC, and then it modulates the volume over time, and that's how it actually outputs the samples. And I'm guessing that's still going to be the case here. So it's really just adjusting these volumes, and then that's how it plays the sample. So I don't expect really anything magical here. I'm basically expecting there's going to be some kind of data pointer into the sample that's incremented every tick, and then it reads some sample, which looks like it's just going to be 8-bit values here, and then just dumps those into the registers, especially because of just how contiguous these values look. In fact, here, they're even a little bit too contiguous. Okay, there it starts to get a little more crazy. Just gonna play this again just to be sure. Gravish, if you go to, I'll actually post a link. So one of the documents that we've been using on the stream is called the Sacred Text Scroll. And it's basically a collection of a bunch of other information, like information from other places in reverse engineering. It's an unofficial doc, which is why that's the one we use on stream. But it has a lot of information on the audio unit. It's not quite correct. There's a newer version of this document that I'm not supposed to distribute yet, so we use that in a couple of the bits. But that'll give you at least a pretty good high level overview of how the audio unit works. Yeah, so these, I'm basically just looking for a lot of variance in these values. Yeah, and I'm seeing what I need to see. So that's good. So yeah, so what I want to do is add a watch point to this value here. And so I'll just AW for add watch point, that value. And now we have a watch point there. So now if I continue, that didn't work. Did we break watch points or something? That was strange. Hey, Recha, how's it going? Looks like the watch points aren't working correctly. Is that something I need to enable now? Do we put that behind a feature? I don't think so. Doesn't look like it. Try later. Those addresses are VSU relative. Of course. That makes total sense. I forgot about that. Yeah, okay. Thank you. Oh, it sounds cool, Ratchet. We are trying to extract some sample data. Figure out what is wrong with these timers again. Yeah, so this is, I believe it's, I'll just look up the address actually. It's in the higher level memory map. Yeah, 01. That should do it. There we go. Boom. And if we continue a few times, we should see a lot of these. Okay. So now we know that this 18A is the actual address that is writing the, where that write is taking place. Now, or actually I think it's right after that, technically, because I think it only dumps the instruction after the watch point happened, just because of the debugger is very simple. So what I want to see is did we already have that here? And it looks like this guy here is the one we're looking for. That seems odd. That seems really wrong. unless this is an offset onto a variable that's on the stack. Because it's, if R3 is pointing somewhere. Wait a minute. Is this reading that value? Or actually, it's probably this. Probably these that are doing those writes. Because these are 64 bytes apart, which we're seeing here. And then if we dump our registers, if we look at R1, R1 is the offset to one of these. Okay, so it's actually these two that are doing the writes. So whatever R8 is here, that's our sample value. And in this particular case, if we look at our prints, we just printed 77 here. If we look at R8, we will see 77 hex. So at this point, we can start adding some of these notes. I'll just add it to the end of this, actually. And I like to just add a lot of information here. Even if it gets to be a lot of like extra stuff here, because it gets harder and harder to like keep this stuff in your head. But this is cool. This was even easier to find than I thought. But then this makes sense, because then that's the last thing this is doing is updating this, and then, yeah, looks like it's restoring registers, and then we're done. So the next thing I actually want to do is see how does it get here. I'm wondering if, if it jumps here, because we saw up here. So this is the basically beginning of the handler. After the little stub that's at the actual handler address that jumps into here. In here, we can see it does preserve some registers, and then it looks like it loads some value here. Now this offset, 0500 in the higher bits, that says that this is going to read from something in RAM. So it looks like this basically reads a value, reads a variable here into R6, or an address, actually, because that's used here. And if R7 is 0, we branch to here, 144, which is here. Now I want to see if that's the case. So that would be the value of R7 in that case, right? Now I don't expect R7 to be, yeah, it's clobbered here. But let's just see if we run through this routine again. So for example, we can add a breakpoint to this again. So now we're entering this, and I just want to see where this steps, right? So we're in this handler, we're 2A, so we're here. We're just going to keep stepping. And yeah, so we're going to load the value here. And if we print the registers, we'll see in R6, there was this address that was loaded. We can also, by the way, we can do a mem dump there. And we can see at that value, there's a 1. Interesting. I'm just going to keep stepping here. And after that, we should have R7 loaded, which is the 1 that we saw earlier. And then it was doing a branch. It looked like, so it did a store for some reason. Not really sure why. And then it would branch if that value is not 0, which we know it's not. So that should go to 144. Okay, so here's what's really cool now. We saw that if that value is, we can basically do this. If byte, we can do this just to have some notation. we can basically do this conditional here. And in fact, basically everything here just checks this condition. And then we branch. And we basically should be able to remove all this, is what I'm guessing. And this becomes our sample playback routine, which is really good. I was hoping this would be this short. Base effect, God bless Ida Pro. Yeah. I think actually Radar 2 has support for Virtual Boy. I haven't tried it though, and it's not really a tool I'm very familiar with. This is kind of a painstaking process, but it's also kind of fun to do with a homemade debugger. So even though it's definitely not the best way to work, I kind of enjoy it. So we'll do that, and then this is our little brace, and then eventually we do return stuff. So we can basically start getting rid of all this stuff. In fact, we can even get rid of this, because I'm guessing that none of these other register values are going to be particularly interesting as we enter this routine here. Because what my guess is, we're basically going to... maybe we have some stuff like in our 6 here. Yeah, okay, so some of this actually is relevant. In particular here. We're going to move that conditional there. And so this actually makes a lot of sense because it looks like we're going to set up some kind of data pointer at R6 here. We store R9, probably doesn't matter there because we're just going to overwrite the value here so we can get rid of this. Dale Collins says, guessing it's a 4-bit delta sample. Interesting. So here we load this value into R1. Now I can't remember what was in the 200 range. Let me actually check our mem map. I don't think that was ROM. Yeah, that was down here with like link control, those kind of things. So it might actually be reading some of that as well. If that's the case, we really don't care. In fact, we can actually probably work backwards just to see what loads into R8. Here it shifts left whatever R8 was by 4. And it loaded R8 here. So we took a word from R6 plus 4 and put that into R7. And then we loaded the value at that address into R8. Would 16 bytes have been enough there? That seems a bit weird to do the full address here. So I think that's a bit strange. But it does look like R8 is loaded here, and then it's not loaded anywhere else. It's not overwritten by anything else. We also have a compare here, which branches to 1AA, which I deleted. Actually, that's out here, 1AA. Let's see if I can just... we can just do this. Just go there and disassemble. Now this might, since I'm seeing a lot of manipulation of R8, this might be significant. But what I think I want to do is set a breakpoint. Actually, where were we? 148, so we were here. Let's just step through this and see if we actually go to any of these other places. Because it's quite possible we don't, although that might be some decoding here. David was 1269. I'm pretty sure that's the timer. Yeah, that would actually make a lot of sense. Up here when it was setting these. At 20, yeah, let's look at the memory map. Timer control reg. Yep, that's exactly what that is. Good catch. Anarchy, thanks for the follow. So here... Actually, it just seems to load... Here we go, actually. So here we load some stuff into R1, and then R1 is used here. Let's do this. In particular, I think we had a... That's just timer control. Okay, that's fine. And then here it actually stores that. And then here it was our 10, which looks like 19. Now, I don't remember exactly how these bits are laid out, but we can look at the timer. So that would have been a 1, 9. Now 9 is 8 and 1, and then there's 1 in the high nibble. So we have the timer interval, which is the small interval. So we expected that. Enable is this shift right 3 and 1, which is going to be the 8 bits, so it is enabled. Oh, that's 0 interrupts and timer enable, yep. That looks about right. Now this makes sense because this basically just resets the timer. Actually, there's something really interesting about this code. All this does is reset the timer instantly. So there's no time between when it shuts off the timer, does some stuff, and then re-enables the timer. So just like the testing showed this weekend, the CPU cycles is not actually significant for the timer playback if this is the only place where it touches the timer, and I'm guessing it is because there's not a lot of code here. So that's actually pretty interesting. But that's something that I expected to see today. So that's good. Now, all right, here, it compares, I guess, the sample value to 15. And then if that's what it is, it goes to this value. Otherwise, we compare R10 to 0, which it's never going to be. Unless R10 is adjusted by this routine and then it branches back here. So this is probably going to be significant. Yeah, we're going to need to kind of dig into there to see maybe what these are doing. And the reason is because I want to actually try and extract the data of the sample, not just look at the play routine. But we can still assume that after that, R8 is shifted left by 4. I'm not entirely sure what it's doing here, unless, again, R7 is the sample pointer, which this could make sense because we read... Just looking at this again. Into R7. Yeah, so this R7 here is different than this R7 if you look at the lifetime. But this basically takes R6 plus 4 and puts that into 7, loads that word, and then here it looks like it increments it and then stores it back there. It also adds 31 to R10, which may or may not be significant. We're not sure. But I'm guessing because of this line here that R7 is going to be our data pointer. Now, if we, again, dump the registers and we look at R7, we're seeing not a lot that looks particularly interesting, but that's probably because we're, probably because we're at 148, which is here. If we go to here, actually here, 150, then R7 should be interesting. FFF1B14E is one value that we've seen there. Now, this sample, because of this other stuff I'm seeing here, might actually be compressed. Although I'm not entirely sure if it is. But we don't really know what that stuff's doing yet, so that's why I'm not really sure if this is the sample data pointer. And we also just don't know that for sure yet anyway. But actually, I don't want that alignment. That's sort of speculative what's going on. Assuming that's true, we're going to have a couple more bits of information here. So here we know R8 is the sample value. And because this is linear here, we know that this is going to be like that. We know that for sure. Now, I want to actually just step through this to see if we go into any of these other addresses here. So now, by the way, R8 should be 77, which is, did I get that right? Excuse me. Now, R8, so compare 15 to R8 should actually be comparing those values directly. Yeah, so we don't get that branch there. And we compared R10 to 0. Not sure what that's doing yet either, and then we don't branch to there. I'm just trying to see like how much of this can we ignore. But in this case, we had R8 and then we shifted it to 770, which 70 is probably the value we end up writing to the register here. And that would make sense because, yeah, so we store byte and then that's just going to store whatever byte this is. So at least in that iteration, yeah, there we have the 70 writing here. In that iteration, we didn't hit anything crazy. Yeah, if I just keep stepping, we'll get something else. Just a few of these iterations just to see what's going on here. Looks like they're all basically taking the same code path. Code path, not code bath. Code bath is what we're taking right now. Deep dive. So another thing that I'm thinking I kind of want to try here is setting up breakpoints at these addresses to see if they end up being significant while this sample's playing. Just to see if we even ever hit that. In fact, we can remove the breakpoint here, and we can remove the watch point here. Okay, so there we did hit it, by the way. And this was this one, actually. Oh, these are actually right next to each other. Did not realize. So we're probably going to have to take a look at this a bit. Looking for these branches here, those are going to be convenient. But it looks like there's some other ones here as well. 1 EA. Let's just grab a chunk here and then take a deeper look, a closer look. One A6. So again, I also want to just step here. A8. And that went to 7E, so that's here. And then we're gonna store everything. And I actually wanted to bring some of this back. Here. Just so that we have the continuity here. Because it looks like if we look at 1.6 here, that's just going to increment R10 and then branch back to 1.7 here. And this is basically never going to be used. Yeah. I don't know what's in R10 still. Let's separate these a little bit. This is interesting as well. Because in this case, it looks like we load R7 offset by 1 into R8 and then compare that against 15 again and do some other things. 1C6 would branch us here. 164 would take us back here. To do this compare again, interestingly enough. Very interesting. Jay Westfall, you want me to make a temp branch with my CPU trace junk? Should be easier to see what's going on. Yeah, maybe that's helpful. I'm going to feel like an idiot bumbling around with the trace stuff that I'm not that familiar with. So, if I don't want to use it yet, that's why. But I probably wouldn't mind giving it a shot. I mean, at least that'll help us see the values change over time. We're seeing, though, there's definitely some adjustment of R7 again here. Which, again, is probably... So I'm guessing that R7 is a data pointer here. Some kind of data pointer, but this may be like compressed data. 15 hex, by the way, is 0F. And the reason I'm putting that in there is because that'll make that a little bit easier to understand that that's, once you see that that's 0F, it makes it a bit more obvious that that's some kind of like escape code. So I think that's what we're seeing there. Yeah, because here it also adds 2 to R7 after we've read the first byte and then the second byte after that pointer and said that they're both FF, or that they're both 0F. Now, I don't really know what happens next, because here looks like we use R1. What's 404? Is card expansion even? That seems wrong. It could be plus, yeah, because that's plus R9 into R1. Could be what's 404 in our voice thing. That was the voice 1 volume. Whoops. Sorry, Jay Westfall. I need to add you to the whitelist as well. Let me do that really quick. Yeah, sorry about that. Now you should be able to paste that link, or you could whisper it to me. Either way would work. Yeah, there we go. Yeah, let's give that a shot. Just so maybe we can see the actual data moving. Before I do, though, I just want to read through this a little bit more. And we'll give that a shot. It looks like, though, if it's FFFF, this will actually push the data into the volume registers. Is I think what we're seeing here. Let me here. Oops, no. This one. Okay. Voice 1 volume and then the voice 2 volume. Rather than the envelope data, which is what we saw before. You know, that could make sense, actually. Because if this were... So here's what I thought was going on here. I thought originally that this would be just setting the voice volume for each voice over time to play the sample. It looks like, though, that what we found here is this is an escape code where it won't actually... So it's probably normally writing the envelope data, which is going to allow it to ramp up and down, probably between samples, which could actually make a lot of sense for this kind of routine. And also because we saw so many similar values over and over again. And then it looks like we found here an escape code that would set the actual volume to this value. Yeah, so if it's... Let's see if we can add some notes for this. So for example, we have a data stream. So we have different bytes, and if it's basically not 0x0f, so let me try to think. How do I mark this, by the way? If I'm just gonna mark some numbers. Do like ZZ or something. That's actually wrong. Let's do fat arrow, and then we'll do this assignment syntax. And this is going to look like, it looks like, so this is the case where we had the sample, or the next byte in the data stream was 0x0f. Then we went to here. I'm kind of ignoring R10. It looks like that's just some preservation stuff. Yeah, then it loads the next byte. That next byte, where that's also not FF. Then, yeah, because if it was, it would branch to something else. Then that's just the voice volume, and we store that. And we load the next value for the envelope. This is cool. Why don't I know a notation to do this just for some number here? Let's just do XX here. And we'll do, yeah, that's fine. And then we'll do, because we need here. So we do like that. Now the next thing is that we need this last case where it looks like we had like that, and then I don't know what comes after that. So that would be the case where we had R8 was OF here, and we went here. It was that again, and we're here. Now R1 here is still 404 here, because this is being used in either case and it's not overwritten. So here it still sets the voice volume. Does it reload that value, by the way? It should reload R8 here. Down here. No, it sets it to 0. And then does this reset the data pointer? No, something in R7. This looks like it disables the timer. I think that means we're done. Dark second is a sample. Yeah, that's what I'm thinking, because it looks like if we go to 18 here, if we look in the other memory map, is a timer counter reload actually? I would have expected to see it stop, but it could actually be something else. It might actually use a small timer interval for the rest of the audio playback. So it could actually very well be that it resets it and then we're done with the sample. Let's assume that that's what it is for now, because that would be pretty sensible. And then we'll see, because it doesn't adjust the data pointer and then it exits. So that's probably end of sample. So then this should be a pretty straightforward data stream. And then we want to find out where it starts, probably. We also want to look at the timer values. But generally, it looks like it doesn't actually adjust the timer values at all, which is really good, because we should be able to at least figure out how often these register values are set. Unfortunately, because this is not just straight up sample values, I don't know how effective we'll be at actually extracting the sample itself. But we should, yeah. Because I'm just thinking, if this is what we end up seeing more often than not. Actually, let me look at what the envelope data did again. Been a while since I touched that. Where's the envelope? We get a reload, we get a direction, and we get a step interval. And then it resets the level. We could actually just try to extract this data and just assume that the reload value is all it does, and then we don't do the ramps when we do the extraction. And with that, if everything happens at a constant rate, we should still get something that resembles the sample. It'll just probably be a little bit garbly. But that would be fine for us to, like, here's my hope. My hope is that we can basically get the sample data out and put it in a WAV file, and then adjust the sample rate of the WAV file until we figure out what that sample rate's supposed to be, and we'll compare against the recording from the hardware. That should tell us what the actual sample rate is, which is how often this timer ticks. And it looks like if we interpret the data that way, while also basically respecting the compression routine that's here, that should actually make sense. But I'm going to be right back. I need to use the restroom, and I'll think about this a little more. So I'll be back in about 5 minutes. Okay, so if this is going to be the sample format, the next thing that we basically need to figure out is where the sample starts and where it ends. Now, to do that, I think all we would have to do, because it looks like the whole timer routine, it only runs this bit that we're interested in here when it's playing a sample. So my guess is that if we set a breakpoint here before the sample starts playing, so what I'm going to do is I'm going to reset the game. And we're gonna set a breakpoint here before the sample starts playing. And we shouldn't actually trigger the breakpoint. And we're looking good so far. There we go. Perfect. So that's what we expected. Now, what that tells us is that something just changed to make this work, and R7 is very, very likely after this point. So we'll step a few instructions. R7 at this point is likely going to be our initial data pointer. So that's cool. Just for kicks, I'm going to reset it and do it again. We're actually going to set a breakpoint here because that's where R7 should be set. And we should get the same thing. Also, what I think I'm going to do is have the game play a different sample. And we should get a different value there. How cool is this, though? That looks like the same value to me. So that's our initial sample pointer, it looks like. Yeah, let's go ahead and we're going to get the game to play a different sample. The game plays a few different samples for different tables. Like as in pinball tables. I think they're called tables. And so I'm going to have the same address here. We're still seeing a lot of different register writes, but that's because it's playing music during this part. So if I just pick like any one of these, we should get it breaking right about now. Perfect. And then here, if we do registers, R7 is here. So we could say, welcome to Space World. List a couple of these. Cosmic. So those are a couple data pointers. Now, what's really cool about these, by the way, is we should be able to basically map these to ROM addresses. And I'm guessing what we can do is basically write a small Rust program that's just going to sit here and basically run this decompression routine and just dump the samples into a WAV file. Now, it should be pretty straightforward because we basically should be able to give it the ROM and this, and then we'll do just enough memory mapping for it to actually read samples from ROM. I basically did this when I reverse engineered the Mario Tennis decompression routine. So I actually have some code laying around for that. Let me see if I can show some of that. It's getting a little bit late, so I'm not sure if I want to dig into this right here on the stream. But let's just see if I have the other code that I had from before. Because we may be able to use that as a starting point. Yeah, this was the Mario Tennis code that I reverse engineered. And that was done using this same process, by the way. But I was trying to understand like every little bit on a deeper level. And of course it was a decompression routine, so it was a little more intense than, or well, I mean, this is a decompression routine. No, probably not a decompression, but like a different kind of playback routine. But Dark Second, can you look at the data in the disassembler, see if it looks right? Yeah, I can do that. That's a good point, actually. If we look at, oops, here, we should just be able to do this. Go to this address, and we do MM. Yeah, so now we're seeing a lot of like the 77s that we saw before. We should eventually see some 0Fs. Although I'm just eyeing it, so might miss one. I mean, it looks to me like it could be sample data. Anyway, it's at least in the right range of values that we saw before. Of course, remember, these will all be shifted. So I'm not actually sure why they use these values even. Because it just shifts them anyway. But I want to see at least one OF. Let me double check the code actually to make sure that that's what it was checking for. Here. Yeah, compare immediate would have been this, so 15 to R8. Which would have been that exact number because when you do BZ, the 0 flag is set if they're equal. Like in many CPUs. So we're looking for specifically 0F, not anything shifted, because it doesn't adjust the value of R8 after that. The nice thing about this, though, is that it seems like that is a pretty special case. Kind of weird we haven't seen it yet, but all the values do look to be in the right range, at least in terms of the register values we saw before. Oh, here we have FFFF. There's a couple more of those. EFFFF. Maybe that's just one of the values. We could also just be looking at bogus stuff by now. But judging by where this other sample was, these could be pretty big. It is also a bit strange that they even have data in the upper bits when they seem to just shift it anyway. But that's what we're looking at least. You know, another thing we can do actually, oops. Big errors when you don't put something correct in the debugger. I was gonna actually just do this because we basically know, or we're assuming, 1C6 here is the the stop condition. Ha! Cool. This was, by the way, the end of the cosmic sample, but it totally played the sample, and then we broke there. So if we do register dump, R8 should give us 0F, like we expected, and R7 should be almost the last byte, except this R8 here was actually from this +1. I need to reset the game and then go back here. Here. Then Colin, you should see it fade out at the end of the sample data also when you look at the memory. Yeah, that's a good point. Let it play the sample and then it should break. Good. And then if we look at the registers, R7, this value +1 should be the end of the sample stream for this one. And again, that's +1 because of that, because of how the 0Fs were read. So actually, if we go to this address here and we do a mem dump there, we should see 0F in the first one. And actually, if we go to one before this, we should see 2 0Fs. Oops. Oops. 2 0Fs, just like we expect. And in fact, we can go, just as Daniel Collin pointed out, if we go, whoops. If we go a little bit before that, for example, I don't know, 5, let's do like 40. Really? Oh yeah. Then we have FF here, and this to me does actually look like a fade out. Ha! That's pretty cool. Actually, here's the other thing that's interesting, because these, if they're interpreted as like those literal bytes, these would end up being the those envelope reload values, and it only seems to affect the upper bits. If we look at the registers again, the data registers, the reload is the upper 4 bits. So it looks like it just sets the reload values. And the direction and step interval end up being 0. Now basically because the step interval we do have a data direction, which is going to be 0. Yeah, so it still does seem to ramp these. And data direction levels less than 15. Not data direction level is greater than 0, then it ramps it down. Seems to always ramp down is what these values would tell me, since we know it's shifting those left by 4. But what we showed here is that we're able to disassemble enough of this playback routine to basically figure out the data format and where the sample starts and end. And we found at the beginning of the data pointers, we saw what looked like good sample data. And at the end of those data pointers, we also saw the expected end of data bytes that we expected. And also, as Daniel Collin pointed out, we saw actual volume ramp. Yeah. But by the way, Jay Westfall, sorry I didn't end up using the tray stuff. I don't think we'll need it after all. But thanks for uploading that to a branch. Appreciate that. That's really, really cool. Anyway, I think as it's about 9:30, I think I'm actually gonna cut off the stream for now. So I'll probably end up doing the actual Rust implementation of this decoder off the stream and later at some other time. Probably won't do it right now. But I think this was kind of the more valuable part of this exercise, at least in terms of extracting this data, because we were able to, get it from the disassembled code, which is pretty cool. Thanks, Nerd Delta. I'm really happy to hear that you guys like the stream when I do stuff like this, because this is the kind of stuff that you'd like never see people do when they're working on emulators. You see the results of this work, but I don't feel like I've ever seen people do this work in particular. So I think that's kind of cool. Even though it can be pretty slow, at least it was relatively straightforward. I also think we were pretty lucky that this sample playback routine was as simple as we expected, other than the fact that it looks like it's actually ramping the sample values rather than just setting them all the time. So that's pretty cool. This is one of the more hardcore programming streams. Really cool. Thanks, man. And that also is a comment that makes me really happy, because that's totally one of the things I wanted to do. A lot of people do live coding streams and they do things that like they're really comfortable with because they feel like they want to be good teachers and teach that really well. But I think my stream is more, let's just do something cool. And even if I look like an idiot, at least we're doing something cool. So that's cool. Anyway, really glad you guys enjoy that. Appreciate that. I'm going to call it quits for tonight. And thanks again for watching. I did actually, by the way, remember to record this stream. So that'll be uploaded. That'll be published tomorrow evening. If for those of you guys that caught my demo scene stream on Sunday, there will be another one this Sunday. And the reason I haven't uploaded that to YouTube is because I forgot to record and the stream cut out midway. So I actually have to download the Twitch files and then stitch those together and then put those on YouTube. And I'll probably do that, I don't know, maybe tomorrow. I've just been really lazy about that. But that is coming, so I will have a recording of that, and then I'll have a recording of this tomorrow pretty quick. So anyway. Cool. All right, thanks again, guys. I appreciate it, and I will see you next time.